Swayam Prabha. Digital India. Educated India.
Lecture 2, and if you recollect in module 7 lecture 1, we discussed about creep of concrete, and at the end we talked about prediction of creep by ACI formula. We will just quickly recap that, but today we will be looking into some issues related to creep and some related to shrinkage. So, we will look into creep, prediction of creep, what has been remaining. Also, we will look into where creep is, relevance of creep in civil engineering, structural engineering, and then we will look into measurement of creep, and lastly some introduction to shrinkage. So, to start with, we will look into the British method of predicting creep, and if you remember, we talked about the ACI method in the last lecture, and where we said that the phi ultimate infinity can be related to some factors 2.35, 2.35, 2.35, K1, K2, K3, etc., several factors. Today, we will look into the other method. Today, we will look into another method. So, that is the British method, and in this one what you do is, first E is determined from equation and ultimate creep from figure. So, E is given as E t 0, that is at any time. Modulus of elasticity is any time is important, because you do not know at whatever time modulus of elasticity is not known. So, it is actually related to modulus of elasticity at 28 days, and then this ratio of the cube strength of at that time to 28 days cube strength. So, this ratio is important. So, this is related to, so 0.4 and plus 0.6 into this ratio. In other words, when this is high, this ratio is more than, it will be more than 1. So, 60% weightage to this one multiplied by E 28, and it gets increased actually, and 40% directly as this much. So, it is this relationship is of this form. Now, E 28 is found out from this relationship, E 28 is found out from this relationship, 20 plus 0.2. So, it is assumed a linear relationship with respect to cube strength simply, with the intercept being 20, intercept being 20. So, it is put in as a linear relationship, and this strength ratios depends upon age. It is 0.7 7 day, 1.17 for 90 days, and 1.25 for 1 year. So, this from this first you find out the E corresponding to E at that time. Now, once you have done that, then you can use this diagram. Now, if you look at this diagram, in this diagram you have got relative humidity percentage here, RH percentage here, then this is the ultimate creep coefficient is given along this direction, and this is for 3 conditions actually, 3 conditions of volume to surface area ratio. So, these are 1, 2 and 3. So, 3 conditions of volume to surface area ratio in millimeter, on millimeter, or in bracket it will be in inch. So, whatever it is, its volume to surface area ratio is like this. So, up to certain value, below 100 mm of below 100 mm of volume to surface area ratio, these values will be ultimate creep coefficient values can be obtained. So, below 100 mm values volume to surface area ratio below 100 mm values, and this is the relative humidity. So, average relative humidity indoor, this is average relative humidity condition, this one is outdoor in United Kingdom, and this is 1, 3, 7, 28, 90, 365 age. So, these are the ages. So, if you have age, say for example, this is a kind of nomogram. Let us say I have got 60% relative humidity, 60% is the relative humidity, and I am interested in the ultimate creep coefficient in 90 days, then I come to this curve, and then my volume to surface area ratio is, let us say, it's between I mean below 200, above 100, but below 200, and this is more than 200. Let us say 150 mm. So, my V by S is 150, just hypothetically. RH is 60%, and I am interested in ultimate creep coefficient, creep coefficient at 90 days. So, what will I do? 60% relative humidity, go to 90 days, go to 90 days, go to 90 days, come along this direction, and it is 150. So, it is somewhere in between. So, it will be given as 1.6. So, it will be given in 1.6, ultimate creep coefficient will be given as 1.6. So, basically you can find out using this nomogram the values of ultimate creep coefficient, all right. So, values of ultimate creep coefficient can be found out using this kind of a nomogram, which is there depending upon the relative humidity, age. So, the factor that has been considered here, if you see, it is the age, volume to surface area ratio, and relative humidity, right, relative humidity of exposure. So, exposure condition, volume to surface area ratio, and age, these are the three main factor that was considered in this one to find out the ultimate creep coefficients. So, if you know ultimate creep coefficient, then you can find out ultimate creep function, which you have seen in the last lecture. The formula is same, it is the same because the definitions are same, right, definitions are same, there is no variation in the definition to ACI method or other method. So, we find out creep function from creep coefficient, we find out creep function from creep coefficient, all right. So, ultimate creep coefficient can be related to creep coefficient at any age, same similar kind of formula, same basic concept that was there, and then it can be related to creep function as we have done in the last lecture. So, you can predict by using either of the method, but obviously with modern days with Excel sheets available and all that, it is fairly easy to use the factors k 1, k 2, k 3 etc., and simply multiply them by 2.35 to find out the ultimate creep coefficient, which can be finally related to the creep function in the similar manner as we have done in the last class. So, that is related to prediction of creep, and now let us look into measurement of creep. Now, measurement of creep, the standard that is the only standard perhaps is available is ASTM C512, and what it suggests is that you stack cylinders 4-5 of them, and they are subjected to sustained loading and strains are measured. I mean, it will look something like this, like you have a loading frame, the loading frame is here. So, that will have some sort of a some sort of jack plates, loading frame, it will have some sort of jack plates, lower and the upper one, and through which you apply actually load onto, these are the concrete cylinders, and there is a plug in between gap, right. But the main issue is this is almost schematic, and there is a spring below, So, you apply actually load there is a spring below, there is a load of series load apply in series to set of cylinders, and there is a concrete plug at the top, and there is a plug between the cylinder and the jack, etc., and also between the spring and the concrete, which I have not shown here. And then you apply load like this and keep this load sustained. Now, the deformation that will occur will be absorbed by the spring, will deform by this amount. So, there is no chance of load getting reduced, because spring will provide the kind of reaction that is required. Now, what do you measure? You put actually strain gauges, you put strain gauge or any varieties of gauges actually has been suggested. You can have varieties of gauges here in the gauges in the central portion. I mean, you can actually put in gauges, strain gauges, or all kind of gauges are possible. You can insert them, put it into the surface, or even embed them. So, all possibilities are given in the code, and if you look at that, that is all available, and that is how creep is measured. That is how creep is measured. All right. Now, this is costly, it is large and expensive, especially when you are trying to do a number of such cylinders, because it is a loading frame. So, it is expensive, but possibly the only standard method available for measurement of creep. Now, you have to also do one thing. You see, this there will be other factors which would be affecting the creep. So, therefore, you have to have controlled specimen, which will be subjected to similar environmental and such other condition, and the strains there also, change in strains there also will be measured. So, the comparison will eliminate out all the other factors, effect of other factors. So, difference between the strains will be attributed to creep actually under the sustained loading, So, this is one of the setups that has been used. For researcher, they have tried to actually adopt somewhat simpler way to subject, that would mean that if you look at this particular dimension of this one, this will be very large, at least something like 2 meters to 1.5 2 meters, the specimens, etc., plus a loading frame, the loading frame through which you can apply constant load. So, this is a large specimen and large setup and costly also. Simpler way is to subject 2 concentric cylinders, right, to a constant load applied manually through plates by tightening nuts. Just we will see that. So, earlier one, you have a jack, through this actually you apply the load and maintain that load, right, and you can test a number of cylinders in one go, so stack them and put them together to study. Now, in this one, when you have, so number of samples becomes large in particular case. In fact, a minimum is suggested in the code again, that you must cast at least 5-6 of them, 1 or 2 as control, rest all for testing, and so on and so forth. So, it is relatively large, but as I said earlier, this is mostly, this is the only one possibly only type of code that is available or guidelines available. So, the best way to do is to that only, but simpler way is to subject the concentric cylinder to a constant load applied manually through plates by tightening nuts, as we shall see. Then load is measured using calibrated steel tube dynamometer at 0.2 to 3, 20 to 30% of the strength, and then strain can be measured using gauge like DMEC gauges, etc., but loss of load may take place because there is no spring support system like that is there earlier. For example, it will look like these are the concrete cylinders, these two are the concrete cylinder, this one and this one is the concrete cylinders. These are 4 rods, there will be 2 of them are seeing, other 2 will be somewhere there, and there other 2 will be somewhere there, So, 4 rods are there, and there are plates here, and this can be, there are nuts here which can be tightened. So, this is of course the dynamometer, and these are the nuts actually, which you can tighten to actually stress this. This is fixed here. So, this is the dynamometer, there is a ball joint, point joint. So, as you stress this, as you tighten up this, so this will be stressed. So, it is stressed to around 0.2 to 3% of the 20 to 30% of the strength, and then allow the allow the deformation to occur, and you can measure this deformation again by putting Dimmock gauges here. The Dimmock gauges here will also, dynamometer is essentially for measuring the force, the load or the stress, finding out the stress that will come into. So, this is there are Dimmock gauges, is pre-calibrated, this is very much pre-calibrated. So, its deformation, if you know, from that you can find out what will be the stress. So, the stress level in this one can be found out, stress level in this one can be found out. So, because deformation is known, so strains in this one you can obtain. So, the stress level can be found out because same stress will be transferred throughout. So, one can find out the stress level, and the Dimmock gauges or other kind of gauges you can actually apply in the concrete to find out the strain that would occur. At the same time, you must have control specimen in order to obtain the variation due to temperature and any other aspects that would be there. So, this will be have four such rods, and through which there will be some nuts there also, and that is how you do it. So, it is manually tightened, essentially to manually load is applied manually. So, it is actually a simpler setup, but the problem is, see, there is no spring here. So, therefore, due to deformation, because you do not have a way, you do not have a way to, unless there is a feedback system and you have a way to check that there is the load is same, this will not tell you whether load is remaining same or not, because of some of the deformation reaction might get reduced, and in the process you might end up getting somewhat load reduction may occur. So, loss of load may take place. So, these are basically creep measurement. Not too many facilities are available in many places, it is not a very common facility to have this, but those who are doing research may have to set up this kind of facilities, or wherever people do research, creep research on creep, this kind of facilities. The other one would be obviously better, ASTM 512 type, but something simpler one can also devise. So, this is what is creep measurement. This is what is creep measurement. Now, let us see what is effect of creep. Effects of creep are, let us see what are the effects of creep. First of all, it will increase the deflection in flexural members. You can imagine this. This is my flexural member, and say simply supported system, and I have applied load here. So, what will happen in the long run? The deflection will increase. So, elastic deflection, and later on deflection may increase further. So, elastic deflection and later on deflection may increase. So, this could be creep, this could be due to creep, this could be due to creep. So, this could be due to creep, all right. So, increases deflection in flexural member, that we have understood. So, while taking account of deflection control, the modulus of elasticity value that you take must account for the creep as well, because this is a long run behavior. Because what we have seen earlier was this is your epsilon, this is your sigma, this will be the elastic scenario, elastic, and this is due to the creep at some 7 days or some so the creep will act here, and then 128 days and so on. So, finally, the modulus of elasticity is at this point. So, there is some effect of creep, and it must take into account of it must take this factor into account. So, therefore, deflection calculation must, the modulus of elasticity used for deflection calculation, and the code actually does that. Code takes those values into account. Now, you see the creep results in gradual transfer of load from concrete to rebar in columns. Basically, if you have loaded a column, now the load is coming onto the column, it is coming onto the column. Now, the bond exists, all right, but more this stress more through the more the stress increases or this reforms more, this will have a tendency to transfer this, because they are under same deformation. this materials are in parallel. So, this is your rebar, let us say this is your rebar, this is the rebar, this is the rebar, this is the rebar. So, they will have same deformation, they will have same deformation, they will have same deformation, this two will have same deformation rebar, and this will have same, this is your rebar, this is your rebar, and they will have same deformation, because they are acting in parallel. So, if you have load like this, they will have same deformation, same deformation. So, deformation will be similar. Now, when deformation is similar, the deformation is similar and deformation increases, overall deformation increases, because concrete is creeping, under creep concrete is getting additional deformation. Actually, it would try to induce that deformation, or the deformation to the or the strain to the rebar as well, So, therefore, with time there is gradual load transfer takes place from concrete to the rebars. So, with time gradual deformation, gradual load transfer will take. So, when steel yields further, load is transferred to the concrete. So, only after yielding of the steel, the further load will be transferred to the concrete. So, in eccentric column, creep increases, deflection and effect of buckling. So, now obviously, in eccentric column, where there is a load is coming here, this is your column. So, actually this deflection would, this deformation, downward deformation would actually increase the effect of buckling, because this was bending under the moment, eccentric column. So, there is a PE effect, PE, and this PE would result in bending of this one. Now, creep would tend to increase this bending, and therefore, buckling will be increasing. And again you take it in terms of the the E you take in calculations of all this, modulus of elasticity must take account of all this factor into account. So, this is done while doing in design. So, nothing to really specifically one got to look into, but the design E must take account of all these aspects in the long run, creep effect and so on and so forth. In statistically indeterminate structure, creep relieves stress concentration by relaxation and reduces shrinkage stress. So, in statistically indeterminate structure. Now, what is an indeterminate structure? You have actually restraints, additional restraint. For example, a determinate structure, you will have possibly roller and a hinge here. So, this can move, but you make again another hinge. So, two hinge here, it becomes indeterminate. So, therefore, it is actually restrained. So, statically indeterminate structures are restrained, they are restrained. Now, we have seen when you apply restraint, when you put in restraint, there is some amount of relaxation will occur, So, therefore, the stress in the concrete will actually reduce down, stress in the concrete will reduce down. So, it causes relieving, it causes some reliefs in the stress, right. So, when there is a like basically creep would have caused some sort of deformation, but then this is restrained, no movement can occur. So, therefore, this horizontal movement. So, additionally you will have additional force coming in. So, therefore, this will neutralize the effect of, this will neutralize, I mean this is just as an example, this will neutralize the effect of applied stress, and relaxation will actually reduce, and it will reduce stress concentration. Also, shrinkage stresses get reduced. Shrinkage stress, for example, if you have shrinkage stress in a restrained element, shrinkage cracks would be tensile, because this actually its natural position is here. It after shrinkage it will shorten. We will discuss about shrinkage later on, but shrinked position is somewhere there, but it is restrained. So, there is a tension. Now, this tension gets actually relieved because of tension gets relieved because of relaxation. So, this actually relaxation has actually tendency to reduce all kind of stresses, including in restrained structures, because relaxation occurs only in structures which are restrained, where you are not allowing any deformation to occur. So, they actually reduce down the stresses of all kind, whatever they are, including shrinkage stresses, etc., etc. So, this is the first effect. Then in mass concrete, of course, creep may enhance cracking, possibly by causing more thermal deformation under temperature differential. Now, mass concrete, the cracking comes because this is your top surface of the concrete, and let us say this is your bottom concrete. Now, there will be a temperature differential if it is existing, if there is a delta T exists between this one, which can exist because if T could be higher temperature in mass concrete temperature can be higher, because heat may not dissipate from this portion, the heat may not dissipate from this portion, heat dissipation is difficult, while heat will dissipate from this one, heat will dissipate. So, heat dissipation would occur here, heat dissipation would occur here, heat dissipation, heat. So, heat dissipation would occur. So, heat would dissipate from this portion, while this may remain still hot, this may remain still warmer if I may put it so, warmer. So, this may remain warmer. Result is what? This will try to shrink, 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 and if it tries to shrink, the bottom concrete will restrain it. So, bottom concrete provides a kind of restraint. So, restraint here there is a kind of restraint to that shortening. Now, if this is happening, net effect is a kind of tension, net is a tension. So, the cracks can come like this. So, net effect is a tension. Now, what can happen? There is a temperature differential, there is a tension, and there is no there is a tension actually occurring. So, thermal deformations under the same tension, thermal deformation might try to increase, that means and it is again restrained at the bottom. So, therefore, this might result in causing more thermal deformations. So, it can cause more thermal deformation because it is trying to expand under this, or rather this is trying to contract, and this might try to contract further, over the time period of time. So, there is a contracting, there is a or if there is a tension, it will try to, tension is trying to cause deformation in a given direction. So, under same tension, deformation will tend to increase, So, therefore, whatever the force is, this is causing this tension comes because it is restrained, right. So, basically this restraint still exists, and because of the contracting forces, this may further enhance the deformation. So, essentially depending upon the situation, deformation might this thermal deformation in case of temperature differential, it might cause it to increase, because cracking possibility might increase because of the thermal deformation. Now, it is actually trying to contract, I am holding it in position. So, there is a kind of tensile force acting. Now, since there is a tensile force acting which has a tendency to cause a deformation in the which is actually restraining which is because of the restraint tensile force, which there is a restraint. So, the tensile force comes and concrete can crack under those tensile loading. Now, when you have the sustained, this condition is sustained and no crack has occurred, actually further contraction may occur because of the tendency of the contraction may be there because of the because of the creep itself. It may actually cause under more sustained temperature differential, this effect may get enhanced, and if it has not cracked earlier, might crack later on. So, mass concrete, this can actually, tall building differential creep in inner and outer column may result in additional moments. Now, how does it do? In very tall building, this is your outer column and this is the inner column. So, outer column, let us put it red, outer column is here by red, outer column here is red, and this is inner column. So, this is inner column, this is actually inner column. So, if I look at it, my slab is something like this. Now, the load that would be shared by this column would be coming from this portion of the slab, load will come from this portion of the slab, while this column will share more load, internal column actually shares more load. The contributory area catering to inner inside columns would be more. So, actually it has to share. So, this contributory area that from which the load comes into a inner column would be more, it would have to support more, while as outer column only half of it comes from one side. That means, this is loaded at a higher level. So, sigma 0 is high, and we have seen all our definition was for unit stress. So, if the stress is more, creep strain, final creep strain will be more. So, because our definitions were specific creep etc., all were for unit stress, creep function they were all for unit stress. So, you want to find out the deformation in the long run, more the initial stress level sigma 0, more will be the creep deformation. So, this will be deforming more. So, creep differential creep. So, this will have more creep than the peripheral column, this will have more load sharing, therefore, more creep than this one. Now, what is this result? If it is a short structure, not a very tall structure, it may not have any effect, but if it is a very tall structure, the column length is very, very high. So, this might result in overall shortening of the column, which may be appreciable. This effect is not seen in relatively shorter building, only in tall building, say 30, 40 story building and so on and so forth. One if calculates out the difference in the creep deformation over the long run from internal column and external column, there may be some differences. Now, when you have settlement, differential settlement between inner and outer column, this settles more than this will actually induce some kind of stresses, 6 EI over L square or whatever it is, because of the settlement. So, delta 6 EI is delta over L square, So, if the delta is appreciable, it may induce additional stresses. So, this is one effect. In tall building, this is taken into account 50, 60 story building or similar building 40 story building, one would like to take effect of this one, not 50, 60, 45, 50 buildings. So, RCC building where or similar kind of buildings, this effect might be there. This shrinkage also does affect in the similar manner, but we can look at it in different manner. Loss of pre-stress is other effect. Pre-stress is lost in many ways actually. Pre-stress loss occurs in many ways. First of all, during slippage can occur. You are pre-stressing post tension, let us say is the system where you have pulled the wire and anchored it. Now, there can be some losses right at the beginning. So, there can be loss of pre-stress because of slippage of the pre-stressing wire through the anchor and all that. But creep does cause loss of pre-stress due to relaxation, that is what we have seen in the last lecture. Creep causes loss of pre-stress due to relaxation effect. So, therefore, that is what we have seen. Even creep of steel is important here, because creep is tensioned. So, but it is restrained, its deformation, its length is fixed. Now, due to creep, its natural length will actually tend to increase, but you have restrained it from expanding further. Therefore, there will be some amount of relaxation also. The creep of steel can result in loss of pre-stress, but we are talking of loss of pre-stress due to creep of concrete, and that we have seen in the other day, that relaxation will cause loss of pre-stress. Okay. So, these are the effects, some of the effects and some of the effect of creep on structure. Now, creep is also related to fatigue, which I just mentioned somewhere in the 6th module at the end of the fourth lecture, but let us see how it is related. This is for almost all material, many materials show this kind of behavior. What is said is, if you see, this is time, this is strain, and after loading. So, you have loaded, this is elastic strain, this is elastic strain. So, this is your elastic strain, remember, then there is a creep, but beyond certain stress level, this goes on increasing. We have seen in case of concrete, of course, in normal lower load level, it actually tries to be asymptotic, but anyway the slope has, in many materials slope will get reduced, and it is like a linear constant rate increase, and as you go further at high strain, at very high, at long run at high strain, it may actually result in failure, because suddenly there may be lot of deformation. So, rate might increase again. There is a high rate here, which is tendency to reduce, and here low rate tendency to increase, and somewhere here failure may occur. So, failure can occur due to creep at higher level of load. Now, this is called elastic strain, this is called primary creep. Up to this, before the linear range starts, this is called secondary creep, and tertiary creep again it increases non-linearly, and the failure occurs. So, tertiary creep stage, secondary creep stage and primary creep stage, right. And concrete also shows this behavior about 0.6 to 0.7 or 60 to 70% of the strength. So, therefore, you know where to operate on, that is one thing. So, therefore, primaries and secondary creep etcetera and tertiary creep, that is how we distinguish. So, concrete also exhibit this around 60% to 70% of the strength. But interestingly, you see this as you go repetitive loading, after each step of loading, because it is sustained, it is time, it is also sustained. I mean, you can assume supposing my cycle time is very high, frequency is very low, right, frequency is low. That means, one case I apply, let us say 10 cycle per minute, let us say, for the just for the sake of understanding, or 10 hertz, 10 cycle per seconds, that kind of a reversal of stresses, stress reversal. I have a cycle of stress, and I just I have a cycle of stress, and let us say one cycle of stress going to maximum compression to tension again, and this let us say finishes in constant, let us say, or even sinusoidal or whatever. It is rectangular I am showing, but it can be triangular or something of this kind, some sort of cycle of stress I am applying. Now, you see this, let us say, is 10 seconds, then think of this being 10 hours or let us say 10 years. Now, one cycle in 10 years means there is a constant load is there, load is sustained, but the value is changing, the value is changing. So, fatigue is a case, reversal of stresses occurs at a very fast rate, cycle time is low, but if the cycle time is infinity, it is actually sustained loading. If the cycle time is infinity, that is very long time to complete the cycle, practically my load is constant. So, therefore, that is actually a sustained loading. So, there is a relationship between sustained loading and fatigue. So, when I have reversal of stresses, so it goes to a it goes to minimum, but then the load is still sustained, it is not gone away. So, when I come back, I do not come back to again this point, but I come back somewhere above, because load has been sustained for certain period of time. Second cycle, so cycle time is less here, small, its frequency is cycle time period is small. So, 1 over time period, frequency is very high. So, very high, low frequency, extremely low frequency, 0 frequency is sustained loading, low frequency, 0 frequency is sustained loading, high frequency is a kind of fatigue. So, repetitive reversal of stresses. So, now next time it comes here, then again I go back, come back, it comes here. It does not come back to its original state of the strain actually, it will not come back to your original state of the strain itself. So, basically because it is under sustained loading. So, slope of this line is same as the secondary, slope of this line, it is somewhat related. The slope of this line is related to secondary creep stage. Therefore, one can relate the fatigue strength or number of cycle it can withstand, number of cycle it can withstand, to the secondary creep rate, So, this is the secondary creep rate, strain per unit time. If you look at this strain per unit time, so one can relate this, and this is what has been done experimentally. People have tried to find out for concrete as well, tension or tension and compression for various kind of materials, one can think in terms of this. So, number of cycles to failure is in terms of log scale 10 to the power 7, 10 to the power 6 etcetera, that is related to secondary creep rate in log scale, again secondary creep rate. So, it is per unit time, So, it is seen that when your secondary creep rate is high, the number of cycle, the failure to the cycle is low. So, it is related to linearly related to, one can approximately linearly related to the number of cycles at failure, So, this is related to the secondary creep rate. So, creep and fatigue are somewhat related. Okay, we did not discuss this. There is something called Miner's rule in fatigue, although we are discussing creep, but I like to just come back and discuss about this. This it is a kind of damage theory, a cumulative damage theory. So, let us say N 1 is the number of cycles to failure, number of cycles to failure at certain stress level, or reversal of stress level, certain stress level plus reversal, and N2 is the number of cycles to failure in another stress regime, if I may say so. In the first one I am going to some level of stress and coming back, in the second one possibly I am going to compression and so on and so forth. So, there is a regime could be different and it requires N2 to failure, N3 similarly another regime of another a cycle of stress, the amplitude of the stress could be different, time period could be different, and corresponding to failure is this. Now, I have subjected, so cumulative damage, supposing the structure or element of the structure is subjected to n1 number of cycles in a particular regime of stress reversal, whose number of cycles of failure is capital N1, then this is the damage. So, damage is N1 divided by N1, where this is the number of cycles till failure and this is the cycle actually I have applied. So, the fraction of damage is given by this. Now, the fraction of damage for another regime is this. So, when this sum total of k such regime is equals to 1, we say that failure has occurred. So, therefore, this is minus rule. So, fraction we can cumulate the damages, this is the damage, this is another damage and this is another damage in another stress and this is another damage and so on and so forth. So, when in sum total the all total of fraction of damage as soon as it becomes 1, if as long as it is less than 1, no failure. The moment it is 1, actually the failure would occur. So, this is what is minus rule. So, when cumulative damage is equals to 1, the failure would occur. Now, what is relevance actually? What is relevance? How it is useful? Supposing I know I have subject my let us say in a bridge, I know the vehicular load, its pattern was available now till date and n1 number of cycles have actually has occurred under that kind of load. Now, suddenly the load has changed, the pattern has changed and we know corresponding to this failure number is N2 and N1 is the number of cycles for failure in the so far whatever has been happening. So, now I want to find out how many years or how many number of cycle it can withstand. So, what I know is N1 by N1 is known to me and plus N2 which is my unknown, N2 divided by N2, this must be equals to 1 for failure. So, N2 is unknown, and that I should find out. So, N2 is actually unknown. So, I can find out the number of cycles that it can withstand in future. So, residual number of cycle or residual life if I may say, or residual damage that is possible or residual life that is possible under fatigue situation I can really find out from this. So, this is minus rule which I thought should be important for us. So, these ones can be these n values can be found out from SN curves, from strength versus number of cycle curves which we have talked about. Alternative approach is to use secondary creep rate, that is a measure of partial damage. So, secondary creep rate we have seen, where secondary creep rate if it is known, then number of cycle depending upon the creep rate, the number of cycle it can actually withstand, that we can find out. So, under a given load what is the creep rate, that if I know under a given static sigma 0 what is the creep rate for that material, if I know secondary creep rate, that can be related to n number of cycle n capital N, that can be related to capital N and then one can find out. So, this is minus rule. So, this is related to creep and some related aspects we discussed. So, this is all about creep. We can now just introduce the shrinkage for this class, while we will discuss it in details in the next lecture. We will discuss it in detail in the next lecture. Now, why does shrinkage occurs in concrete? So far we have seen deformation is increasing. So, its compression, the creep under sustained loading, it will further differ. Now, why creep and shrinkage is put together? Both are related to gel pores and perhaps mechanism one can look into movement of water from the gel pores. We have looked into creep and we said that it is essentially movement of water, interlayer water and so on and so forth, either within inside relocating itself. So, therefore, the bond can get disturbed and slippage can occur and then it can re-establish itself and so on and so forth. That is what we have looked into, right. Now, of course, it is somewhat similar to long term consolidation in clay, the creep, because consolidation takes a very long time. So, you have the load, immediately there will be some consolidation, but the water moves out, and further some analogy right. Now, shrinkage is also movement of related to movement of water from the gel system, and that is why they are studied together, they are put in the same module. So, why does shrinkage occur, or when does shrinkage occur? First of all, in concrete shrinkage occurs due to hydration process, loss of water due to, and also due to loss of water due to evaporation. So, hydration process causes some amount of shrinkage, which we have seen it somewhat, we will be looking at it again, and evaporation loss of water would occur both in plastic stage of concrete and later on in the drying stage of the concrete as well. So, first is the plastic stage, there could be some evaporation, because the bleed water might come at the top and subsidence might occur, plastic settlement might occur, and obviously that is also a kind of volume change, and then later on also evaporation can occur. But right in the beginning, because of hydration process itself, the volume of the hydration product is lower than the original volume, there is some shrinkage which occurs. So, that is what it is. So, volumes, generally there is a volume strain, it is not actually linear strain, it is essentially volume strain, volumetric changes are occurring. But we measure the linear strain, and the shrinkage, when we talk in terms of linear strain, that is in micro strain 10 to the power minus 6, order of 10 to the power minus 6. So, we measure it that way. So, that is what I said, volume of hydration product is so very in the beginning volume of the right in the beginning of the hydration process, volume of the hydration product is smaller than the volume of the unhydrated cement. We have seen that while we looked into the cement hydration process, and we actually calculated that as 0.059 Ch or 0.06 Ch, if you remember, and that is what is chemical shrinkage. So, what is it actually? Volume of the, if you recollect, if you recall back, this was your volume of unhydrated cement, unhydrated cement basically C plus W, and finally, there is a reduction in the volume. Finally, there is a reduction in the volume, there is some unhydrated cement, there is some hydrated cement, and there are all those put together, but there can be some loss of some volume reduction was very much there, even at what we have seen earlier. There is some reduction in the volume, and this volume reduction, this reduction in the small volume, that is actually chemical shrinkage, that is chemical shrinkage. So, there are several components of shrinkage, this is chemical shrinkage. So, chemical shrinkage actually one can estimate how stoichiometrically, using the stoichiometry you can actually find out the product that would be formed from different compounds of cement, C3A, C2A, C3S, C2S, all major compounds of cement, or even our other smaller attringite formation and so on, which actually causes a volume expansion right in the beginning within the structure. So, total volume change actually you can find out, and original volume of cement and water is known, because specific gravity of cement is known, water is known. So, therefore, what is the reduction in volume one can find out because of the chemical reaction itself, and that is called chemical shrinkage. So, this can be estimated, this can be estimated, this can be estimated, chemical shrinkage can be estimated. Then there is something called autogeneous shrinkage. Now, it is actually some volume change occur to the even this is also relatively early stage in a macroscopic, it is a macroscopic reduction in length under constant temperature and without moisture migration to or from the concrete. So, if you seal a specimen, so that no water can go out of it, no evaporation, nothing is occurring, and it is maintained at constant temperature, also then there is some amount of volume change can occur, and that is called autogeneous shrinkage, because a plastic material is now changing into a solid material. So, there is some volume change associated with this, and this is it is changing into a solid material. One is a chemical reaction, other is a plastic material changing into a solid state, and therefore, there is some amount of volume change. So, even if you seal it, do not allow water to go away, no loss, but these are more of so this is still volume change in occur in paste, and they can result in some sort of cracking and all that, as we shall see later on. So, this is autogenous shrinkage and chemical shrinkage, and plastic shrinkage is also a terminology used quite often, because for practical use, practical point of view, understanding point of view, chemical autogenous shrinkage, they are very useful. But when it comes to practical point of view, you see the volume change that is occurring during the plastic stage is the plastic shrinkage. So, it is the volume change that concrete undergoes during the plastic stage, and usually that could be due to loss of water by evaporation. So, what you will have something like this is your concrete, and because specific gravity of cement is 3.15. So, it will have a tendency to come down, and water has a tendency to come up. So, you will have water coming in, you will have water coming in here, and accumulating bleed water. And if it evaporates, or even otherwise there is no bleed water, but some water evaporates from here, more water will tend to move upward, and therefore, the solid will subside, settlement to occur. So, therefore, there is a volume change associated with this because of loss of water by evaporation, and quite often this is actually referred to as plastic shrinkage. Now, the settlement has got a role, in fact, it can cause cracking. Plastic settlement can cause some sort of cracking, I think I mentioned some day earlier. All right. Then drying shrinkage. Drying shrinkage occurs in hardened concrete as it is drying. So, once it is solidified and now it is hardening, at this stage if there is evaporation loss, the actually loss of water from the gel system can cause shrinkage, and this is called drying shrinkage. So, later stages drying shrinkage would occur. Drying shrinkages occur because of the evaporation loss, loss of water due to evaporation, and this can continue for months, 1 or 2 months in fact, and within 6 months, of course, by and large this will be complete. And this is one of the reason for cracks in many thin sections. Right. So, let us see plastic shrinkage more. Plastic shrinkage is due to loss of water at 20 degrees centigrade and 50% RH. This diagram shows this. This for cement paste, and you can see in the x axis is time in hours. So, time along this axis, time along this axis, time along this axis, and time along this axis. Okay. So, time is along this axis, all right, and time is along the x axis, and y axis I have shrinkage. This is for paste, this is for cement paste. So, cement paste shows lot more, it is about 3-4 hours, a lot of shrinkage it should show. Initially it is not very much, in fact there can be small expansion also for a trangite and all that formation, and this dotted line shows large quantity of cement in case of concrete. Now, concrete with 500 kg of cement is somewhere there. This is for 1:3 mortar. So, that means you have a lot of cement here. So, cement paste, neat cement paste shows maximum, cement mortar shows somewhat lower, and this is with 360 kg meter cube of cement. So, higher the cement content, more is this shrinkage during the initial stage itself. So, this is plastic shrinkage test shrinkage as has been seen for paste, mortar. So, aggregate has a tendency to cut it down. So, this is plastic shrinkage. Drying shrinkage, there can be some irreversible component in this. Let us see what is drying shrinkage. See, if this is again the edge, this is edge, and this side is deformation. So, you have like this is your T0, and from this point you started drying. So, this is stored in air, and you will find the strain deformation increases, deformation shrinks. So, deformation has increased when shrinking or reduction, we are calling it as this side, while swelling, if you constantly keep under water, it will swell actually. So, swelling will occur, under constant water condition, while if you are drying, it will go somewhere there, So, this is the drying shrinkage, this is the drying shrinkage, and then supposing you put it wet again. So, therefore, then it will come back. So, this is reversible shrinkage, so you have moisture coming in, but it does not come back. So, this is there some amount of irreversible shrinkage. So, this is reversible, and this is irreversible shrinkage, irreversible shrinkage. So, with age, this is elongation, this portion is elongation, this is contraction. So, if you are if it is drying, then there will be. So, at T 0 drying has started, we find that it increases in this manner, but there is some amount of irreversible shrinkage, everything do not come up, because reversible shrinkage, moisture comes in and then re-establishes some of this. So, irreversible component is due to formation of additional bond in the cement gel when adsorbed water has been removed. So, when you have removed the adsorbed water, new bonds have been formed, like we said even creep, So, new bonds would have formed, where water has gone, the bonds have gone, van der Waals type of bonds have gone, but some relocation would have occurred and new bond would have formed. When you add water, this takes, wherever there was no bond, some bond might form, but some cases where new bond is formed, that leads to irreversibility. This leads to irreversibility. Okay. Then we have situations of reversible drying shrinkage, So, you can see that this is the drying that is occurring, this swelling, wet, saturated, and then again I have actually wetted, dried, wetted, dry, and so on and so forth. So, this is drying, this is wetting. So, it will show a cyclic behavior, right. So, this is what it is. Now, carbonation shrinkage occurs. Carbonation is a phenomena where carbon dioxide from the atmosphere reacts with calcium hydroxide to form actually finally calcium carbonate plus H2O. We will discuss this a little bit later more in the context of durability, and this product occupies less volume than the original calcium hydroxide. In presence of water, all this happens. So, there is a shrinkage associated with carbonation process, and if you have measured it, total shrinkage is this one, total shrinkage is total drying plus carbonation, and drying alone, if one measures, will be something like this, right. Relative humidity percent is shown 20, 40, 50, 60. So, as you increase, the volume change occurs like this. So, this shrinkage. So, net difference is the carbonation shrinkage. So, therefore, this is the difference, this difference is drawn here as carbonation shrinkage. So, carbonation shrinkage, and you can see it is maximum around 55% relative humidity. So, carbonation occurs maximum at 55% relative humidity, or 50 to 60, it is at very high level. Low humidity does not occur, high humidity does not occur, because presence of moisture is essential and presence of air is also essential. So, at very high humidity, presence of air is low, this reaction will not continue. In fact, I should write here H2O. So, in presence of H2O, this will occur, and this comes from air. So, therefore, if it is fully saturated, less of carbon dioxide will be available in the air, and if it is fully dry, again relative humidity is low, less of carbon dioxide. So, this is called carbonation shrinkage. We will discuss about this later. This is of course not very important, it is just important, while other two are very, very important, and we will look into those, and one has to estimate them, because shrinkage can cause cracking in certain type of structures. So, that is what it is. So, we have introduced the shrinkage, that is we said chemical shrinkage, autogenous shrinkage, plastic shrinkage, and then we talked about drying shrinkage, carbonation related shrinkage, right. So, next class we will look into factors which will affect the shrinkage: aggregate, water cement ratio, relative humidity, volume to surface area ratio, slump, fine aggregate, total aggregate, air content and cement content. The amount of shrinkage due to carbonation is relatively less, so we will not discuss much about it. I mean, this is not, it is not, but the drying shrinkage really can cause problem. Carbonation shrinkage do not seriously cause problem, not really cause serious problem. The surface concrete might shrink, but depending upon the extent it is, it may cause cracking, but very rarely, this is not usually seen. carbonation has got other issues. So, we will look into this, but drying shrinkage and its how what factors affect it, like these factors we will discuss in details in the next class. So, let us summarize this. What we have to have seen in this class is actually what we have seen in this one is summarized. To summarize this, actually first of all we looked into prediction of creep, BS. Then we looked into measurement, then we looked into effect, and in the process of course, we also looked into relationship to fatigue, Miner's rule, etc., etc. And lastly, introduction to shrinkage, intro to shrinkage. So, this is what was this class related to. So, this of course, is our discussion on creep finishes, but we will continue to discuss shrinkage in the next class, and that is for the day, that is for the this lecture. Thank you.